So let's go ahead and let's solve our first problem in dynamics, a truck carrying a load. So we have this truck and it is undergoing some acceleration here. So there's some acceleration happening. Um, we have this table here. It has my mass 1 is equal to 100 kilograms. Accelerating the static coefficient of friction between the legs of the table and the truck bed is mu s equals 0.3. We want to solve for the maximum acceleration of the truck without causing basically this table here to move relative to the truck, as well as the reaction forces at A and B. Center of mass of the table is indicated at G. So we need to solve our problem-solving algorithm and incorporate all this in there. So first, let's idealize the real system. So we have basically this table. It is going to accelerate on this truck bed. So basically, we're saying it's not moving relative to the truck, but it is still accelerating. So basically, this will accelerate in the same direction at the same magnitude as the truck to make sure that we're not moving. There is still friction that we have to consider in this problem. So we actually have to write those forces out and solve for them. With that, let's go ahead and get started. Coordinate system, we're going to draw it out x, y, our usual coordinate system here. So check, check. The idealization, I don't think we really... One thing I'd say is that we shouldn't worry about like tipping and those other things, but that's a little bit beyond the scope of what we're looking at. Free body diagram. Our body is the table, so we are going to draw our table here as such. Our whole, basically, table assembly. So at the center of mass, G, we're going to have our weight. We're also going to have a reaction force. So normal A. We're going to also have a normal B. And we're also going to have friction here. So we know that we're accelerating in this direction. Our statics intuition, basically, we always want to have our friction point to oppose the direction of motion so that our acceleration is 0. That's going to be a little bit different here, but let's just say that we're stuck, or we want to continue with our statics kind of notation. So mu s at NA, mu s at NB, pointing in this direction. This may not be the right direction, but we'll figure it out at the end if it's indeed correct, or if we have to flip some things. But that's what we've got for our free body diagram. Now, so we need to draw, so this is our FBD. We now need to draw our kinetic body diagram. So our kinetic body diagram, our table is not, again, we're not, flipping here effectively. But there will be some rotation that kind of resists, the tipping here. But we're basically just accelerating. So our body, M, this M1 of our table, times A, some acceleration in the x direction. There's no acceleration in the y, so acceleration in the y is equal to 0. And that's it. This is our free kinetic body diagram. We're not undergoing rotation, so really, this is it. So let's go ahead and let's do what we usually do. Let's write out our fundamental expression. So let's start off with the sum of the forces in the x direction, and we're going to set them equal to this. So, because we have some acceleration in the x direction. So, we're going to have minus mu s NA minus mu s NB basically equals MAX. Good. That's our first equation. Sum of the forces in the y direction, we're going to set this equal to NA plus NB minus weight. And then we know that this is a y, but this is going to be set equal to 0. Now, we have how many unknowns? We don't know NA, we don't know NB, we don't know this acceleration here. So, we can also basically go ahead and now solve this problem, but we need to set basically or calculate, what are the sum of our moments about, basically some point. Right? So we need to say, well, if we have some of the moments about some point, we know that the body, or actually we can even take it, for example, we can take some of the moments about G because we know that that acceleration should be 0. So let's go ahead and write out our final expression. So we need to say that the sum of our moments about our center of mass G must be equal to I, G, alpha, but there is no acceleration here. But we still need to take the sum of our moments about this point here. I also, unfortunately, think that we've lost some information on this. Yeah, unfortunately, this needs to be 0.6. This distance, anyways, here on our diagram. So let's go ahead and let's look at all of the moments relative to this particular point here. So I sub G. So let's go ahead and get started. So we need to look at, all right, let's take, for example, this is my line of action. This is the perpendicular distance right here. And we can now go ahead and calculate. So what is this perpendicular distance from the line of action? So if I'm at the center, and we're assuming it's rectangular here, so it's equidistant. So I'm going to go ahead and, but because again, I have to use my right hand rule, it's going to be minus NA times my normal A times 0.15 meters. And then I can do actually the exact same thing here. Perpendicular distance from this line of action, but now it's positive. So plus NB times 0.15 meters. And let's look at the perpendicular distance from our origin to the line of action for this direction here. And we see that that's going to be this whole distance, this 0.6 meters. And if I try to curl my fingers, I can't really do it in that particular direction. So those are going to be minus mu S N A times 0.6. And the same thing will hold in the other direction. It'll be minus mu S N B times 0.6 meters. So 3 equations, 3 unknowns. We use these nice definitions. Isn't it nice? I mean, again, this kind of problem-solving type algorithm. So let's go ahead and let's define some values here. Excuse me. I'm going to go ahead and shrink this just a little bit. So we're going to say that our mass 1 equals 100. Our gravity equals 9.8. Our weight, we'll just be, since 108, M1 times G. We're going to say mu S. What was mu S in this problem? Mu S was equal to, I believe, 0.3. 0.3. Good. And then we can go ahead and say Fx equals M1 times AX set equal to minus mu S. Actually, US. I'm going to call this mu. Mu S. Mu S is better. Mu S times NA minus mu S times NB. And then we can say, oops, nope. Oops. No, let's do redo. Minus US NB. Then we can do Fy. Let's do Fy equals 0, which equals Na plus Nb minus W. And then finally, we can have Mg equals 0 set equal to minus Na times 0.15 minus or plus Nb times 0.15 minus mu S times Na times 0.6 minus mu S times Nb times 0.6. Let's just look at our equations. Let's see. 1, 2, 3 unknowns, 3 equations. Let's solve them together now. And Fx, Fy, Mg. Excellent. But we see something a little bit odd here, right? So what do we see? What's happening here? So we see this NB and NA. Some of these directions are looking flipped. And actually, let's make sure it's not a math error on my part here. Let's see here. So one thing that we see here is our acceleration is actually going in the opposite direction as what we're pointing. So this has to do with our initial free body diagram. When we're looking at all the forces in the x direction, we know that our acceleration here has to be positive. So mu is fixed. NA, we're pretty sure, our direction of this force is in the minus, so we should actually flip this to be in the other direction. So because this is not really working out in terms of where our body is going to be accelerating, so we actually have to flip it. Let's flip this here in this direction and this direction. And then that's also going to flip, basically, this and this will be positive as well. So we need to make sure that we take care of that. So let's go back through here. F of y, we'll change this to plus. Change this to plus. Then we'll change the NA is still there. B is still there here. We can solve here. We can solve here. And we've got our values now. So, makes sense? So we see now that our acceleration is pointing in the right direction. Our NA was pointing in the right direction, but we have to flip our essentially NB in this direction. So again, I'm making up these numbers as we kind of go along, so it seems a little bit silly, but those are our values. That's our problem solving steps, and we've got it. So again, all it would do is just flip essentially basically the location of essentially where those numbers are pointing. So you can kind of see that. So that's kind of the difficulty, or not, something that you have to consider when you're drawing your free body diagram. Again, in the math will come out fine in the end, but if there's a known acceleration in this direction, and you have basically forces, we know that they have to sum to basically create forces in this particular direction. But again, it'll come out in the math. Follow those problem-solving steps. We had to basically flip, and so instead of pushing up here, in this particular problem, our NB is going to go like this, again, to prevent rotation in our, to prevent rotation in our particular problem. But yeah, so we got those values. Now we're ready to go. And it's, again, to make sure that there's no angular acceleration here. So that's kind of the result of why we're pushing up here so hard, pushing up here, and then we're going to have to pull down here. So it's a little bit of a silly problem, just because of the math, but that's how you want to approach these. So remember, free body diagram, again, if we're looking at the center of mass here, we know that there was no angular acceleration in this problem, so we're able to set that equal 0. This was really the key kind of point. And there was no acceleration in the y for our body, and then we can solve. So we've got this one. You can alternatively solve for the acceleration here, but then you'd have to also basically the sum of the moments about p, but that's going to equal basically it can make the problem a little bit harder in this particular problem. So that would be something that I would advise probably not consider, because you have some acceleration that you're going to have to deal with. But excellent. That's what we've got. So you've solved your first dynamics problems. Congratulations. But let's say we wanted to solve this problem in a little bit of a different manner, specifically not using this definition, but perhaps some of the moments about a point. Let's go ahead and solve this ourselves. So what I'm going to do is everything stays the same, except let's go ahead now and we're going to solve this problem for the sum of the moments about point A. When we do this, it's really, really critical that we look at all the moments. Specifically, we have this acceleration that's occurring here. This is a force. So we have to consider that acceleration and that kinetic body diagram as well when we're looking about some of the moments about here. So we still have our angular, I alpha is going to be basically equal to 0. So again, but we need to solve for some of those moments must be equal to that acceleration, or actually to that force. So this is still 0, but we need to look at all of the moments. So let's go ahead and let's solve this now. So the benefit here is we don't have to deal with this. And actually, I'm going to redraw this diagram just to make it a little bit more clear. So we have our diagram. I'm just going to, actually, we're going to use this here. Here, 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 free body. So we're looking at this point A. We're going to do, I'm just going to draw this schematically. We kind of know this stuff now. And B and A, we're going to have a force here, and we're going to also have a weight here, and we also have that acceleration, essentially RM1 alpha X going here. So if I'm looking at this, I don't have to deal with these for my moments, but I will have. Now you can look at it here. So the perpendicular distance from this line of action is 0, so we don't have to deal with this, but I do have to deal with this distance from this line of action, which will be in this problem 0.3. So it's going to be a positive NB times 0.3, because that's positive. I'm also going to have a minus weight times 0.15, because again, this is going the other direction. I'll have to flip my fingers from A. And we're also going to have, the acceleration is going to be occurring at G as well. So, but this distance from the line of action of this force to here will be the 0.6. And then finally, we're going to have a plus M1 alpha X, because this line of action here will be 0.6 for this distance. And now we can solve this problem. So we're going to take the same code we had up here. We're going to make just a couple changes that we made. So mass at A, and we're going to call this NB times 0.3 minus W times 0.15 plus M1 times AX times 0.6. We should get the exact same 3 unknowns. We should have the exact same answers. And voila, we got it. Fantastic. So that's your solution for your first dynamics problem. So next time, we're going to do a fun problem with a Frisbee. So see you then. Thanks. Bye.